We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are wicked inventions. Coming up, whiskey. Why did doctors prescribe this popular tipple? Telescopes. The cosmic tool that allows us to see more than just light. Coloured pencils. We reveal the connection between ancient Roman paintings and this modern artist tool. We reveal the surprising science and amazing manufacture behind these wicked inventions. For millions around the world, a good glass of fine whiskey can be the perfect solution to keeping warm on a cold winter's night. But what exactly is it, and where did it all begin? Its ingredients perhaps don't sound as appetizing as the finished product. Whiskey is made from fermented grain mash, compiled of combinations of corn, rye, wheat, barley, and other grains. This mixture is then fermented for a long period in wooden barrels, which give it that familiar, rich, smoky flavour. However, distillation is also a key step in the whiskey making process.
So with the distillation process, you heat up the liquid and it will separate the different liquids into ethanol or water, etc. And it does this by them having different boiling points. The steam at these different temperatures will either then give you pure ethanol or water. So in reality, we have different drinks which have been produced from different distillation processes that give you different flavours.
Distillation is a technique that can be traced back as far as the Babylonian empires of the 2nd millennium BC and was certainly a process used by the Greeks in the 1st century AD. However, this early distillation was for ointments, medicines and perfumes and not associated with alcohol. The idea to use distillation to create and improve alcoholic drinks took centuries to form, taking us to 12th century Italy, where alcohol was distilled from wine by monks. However, it is Scotland that holds the crown for the invention of the whiskey we know today. Distillation of alcohol had spread through Britain until in the late 15th century, malt whiskey was born in the monasteries of Scotland. Its popularity as a drink was helped along greatly by James IV of Scotland, who was reported to have a great liking for the tipple, and it didn't take long for the rest of the world to catch on. By the end of the 19th century, the whole world was enjoying the warming delights of whiskey, but the story doesn't end there. Whiskey was such a popular drink that during the Prohibition Era in the United States of America in the 1920s, whiskey was one of the only drinks to be exempt from the law, providing it was prescribed by doctors.
Some of the conditions that the doctors would prescribe for, obviously now we can see were completely bogus. But I suppose in some respects they might not have done you much harm, and it would be difficult in those ages to prove whether it was helpful or not, but you were getting a prescription from a respected doctor. And so therefore it was legitimate. It was probably seen as quite a profitable way of creating a revenue for doctors of that time.
Although its health benefits may be disputed, one thing we can't dispute is the fact that doctors certainly help keep the population's love for whiskey alive. Today the whiskey industry is booming, with many different blends and brands available. So let's see how this wicked invention is made in the 21st century. The Glenfiddich Distillery is located in Dufton, Scotland.
Founded in 1887, the distillery was built by William Grant and his sons with the help of just one stonemason.
They are the only distillery that is family-owned and continue to make their whiskey in the same way they always have.
Our whiskey is made from just 3 ingredients: malted barley, pure spring water and yeast. The rest of it basically is just time.
Coming up, we'll find out how alcohol strength is measured using flotation. But before all that, the first process in the production of whiskey is to mill the barley grain. The malted barley is milled or ground into a fine powder known as grist. After milling, the grain goes into a process known as mashing. 10 tons of grist is mixed with 3 different waters in a vessel called a mash tun. The waters are taken from the local Robbie-Doo springs.
As a young boy, William Grant actually worked the hills surrounding Dofton, known as the Conville Hills. He was a herdsboy or a herdsman, if you like. During that time there, William Grant knew of the beautiful water supply, the Robbie-Doo Springs. We used the water from the very start of the process, right the way through each stage to the very end.
The mash tun is a double-skin vessel which has a floating slotted floor that acts as a drain as well as a sieve. The water goes in hot at 64 degrees Celsius to gelatinize the starches in the grain and activate the conversion process from starch into fermentable sugars.
The waters will go in nice and hot, and that will simply dissolve down all of the sugars. The whole process there just takes 4.5 hours, and it produces for us a very sweet spring water called wort.
After mashing, the sugary liquid, known as wort, goes to the tun room. The tun room has 24 wooden vessels called washbacks, which are made from Canadian Douglas fir. 41,000 litres of wort are pumped into each washback and yeast is added. The yeast converts the sugars into alcohol. The process is called fermentation and will last 72 hours.
During that time, the temperature will rise, getting to around about 33 degrees Celsius. The yeast will just naturally die, but by that time we have an alcohol around about 9.6%, rather like a very strong beer. And this is what's known as the wash.
A hydrometer is used several times throughout the fermentation process to measure the alcohol content of the wort as it ferments. As the sugars turn into alcohol, the hydrometer floats less. The change from the first measure to the subsequent readings tells us how much of the sugar in the liquid has fermented into alcohol, thereby giving us an alcohol by volume reading. Once it reaches 9.6% alcohol by volume, or ABV, the wort, now known as the wash, goes on to distillation. To produce the whiskey spirit, the wash goes through 2 distillation processes. The first distillation produces an alcohol of around 25% ABV. This is known as low wine. The low wine is then put through a spirit still. The liquid is boiled. As it boils, the alcohol evaporates quicker than water. This vapour is then sent through condensers to turn it back into a liquid. When the liquid first runs off, this is what is known as the foreshots. This is unsuitable for making whiskey as the alcohol volume is far too high.
Once your foreshots have run for around about 30 minutes, the stillman will come through. He will take a sample. And once the alcohol level drops to around about 70%, then he'll move the handle, redirect the spout, and that's us now collecting the heart of the run. This is what we're going to take for our whiskey.
The liquid collected in the middle cut now gets taken to the filling store. Here it is diluted using spring water down to 63.5% ABV. The whiskey is put into a cask and taken to the warehouse, where it will mature for between 12 and 35 years.
All in all, we've actually got around about 900,000 casks on site with whiskey maturing. The majority of barrels we use are ex-American bourbon barrels. We do also use ex-Spanish sherry casks. We lose whiskey to evaporation around about 2% a year. Just for the 12-year-old, that equates to us losing 1/4 of every single cask on site. Evaporation is a necessary evil. Lots more esters will be produced. The spirit will become softer. This is where the magic happens.
Once matured, the spirit is brought down to 40% ABV, using more of the pure Robbie-Doo spring water. It is then bottled and exported to over 180 countries worldwide. So there you have it, from spring to bottle. Whiskey surely has to be one of the most wicked inventions. Telescopes have become high-tech wonders of optical engineering that allow us to peer deep into the darkest reaches of the universe, aiding scientists in their quest to understand the complicated physics that govern our world. Although operating on the frontiers of science, the principle behind how a telescope works is surprisingly simple. In simple terms, telescopes allow us to view distant objects by focusing light, meaning an object appears closer than it actually is. The first method for achieving this technique had been credited to Dutch resident Hans Lippershey in 1609. An optician by trade, he took two different sized convex lenses that bent light inwards and arranged them so they focused the now magnified object for a viewer's eye. The first telescope was born, even if the final image did appear to be upside down. A year later, the Italian mathematician Galileo created his own version of Lippershey's telescope, and his work would lead to the first groundbreaking discoveries in space observation.
Galileo was the first person that took the design and refined it. He refined it so that you could have more mirrors and more lenses, and then you could actually magnify and start to look at the moon. And we know this because he's taken drawings of the moon that are accurate that you wouldn't have been able to see with the naked eye. So we know that his claims of using the telescope were definitely true. And from this, he determined that Jupiter had moons, he could see all these things at a distance, and was able to start to work out the motion of planets.
Because light passed through multiple lenses, these refracting telescopes had a few downsides. The lenses used were expensive and complex to manufacture, and even if accurate, the resulting image could be fuzzy and hard to focus. This was because, like a prism, the light would split up and travel in different lengths, meaning it was difficult to recombine into a crisp image. You also needed to swap lenses, depending on what you were trying to focus on. Using mirrors instead of lenses was one answer, and in 1668, Sir Isaac Newton built the world's first practical reflecting telescope. The new development was that reflecting telescopes use concave mirrors to bend the light together, instead of passing the light through a lens like their refracting cousins.
The mirrors were the big achievement because you could then take the mirror, you could alter the mirror slightly rather than regrinding a lens or swapping one out and one out. And you can achieve a much better focal length, and you can also achieve better magnification. The other benefit of using lenses and mirrors is that you can actually build mirrors a lot bigger. And so now modern day telescopes have a massive mirror collector, which then sends all the information back into a focal point in the center in front of the mirror, which then directs the information out, possibly to another collector, and you can use the mirror itself to do the focusing and tuning rather than regrinding or swapping lenses in and out.
So we can now see everything. Well, not quite. Technically speaking, telescopes look at electromagnetic radiation. Light is a type of electromagnetic radiation, but we only see a part of it. A tiny part of it, with some estimates of humans only being able to see well under 1% of the radio waves generated by electromagnetic radiation. These manifest themselves as the colours in the rainbow, but there are much more electromagnetic waves out there that can be useful in building up a picture of the cosmos.
Microwaves, partly the materials that you use in order to heat your food, but they come in as background radiation in the cosmic galaxies. In the X-ray region, we also have stars that give off X-rays, black holes give off X-rays, neutron stars give off radio bursts. All of these have different wavelengths. These different wavelengths need different materials in order to collect them.
In the 20th century, specialist telescopes were created to capture these different wavelengths, such as gamma and X-ray telescopes, but the most familiar to us are large radio telescopes. A radio telescope is similar to the radio you find in your home, but is much bigger, more sensitive, and able to create a visual picture of the signals it receives. But how do we translate this invisible information into a picture?
When you talk about thermal cameras, you're looking at the infrared, for example. We understand that as red is hot and blue and black is dark cold. We know we can't see it. What we're doing is we're taking that infrared and shifting what we're seeing into the visual spectrum so that we can understand it and see it. With radio waves, you do the same thing, you just shift it. With X-rays, you do the same thing, you shift it into means that we can see, because humans can only see invisible light. We can't see radio waves, we can't see X-rays, otherwise we'd be practically blinded with what we actually see, because there's a lot of it coming in.
Arguably the most famous telescope used today is the Hubble telescope. Launched by NASA in 1990, Hubble uses a combination of mirrors and instruments to detect the visible, near-ultraviolet and near-infrared spectrums to view deep into space and gather breathtaking images. In orbit, to escape the light pollution on Earth, Hubble can view galaxies 10 to 15 billion light-years away and is a far cry from Galileo's pioneering telescope. but its work reminds us of the benefits of gazing into the night sky.
One of the benefits has been we've improved materials. We've actually worked out how materials work better, we've understood their scientific properties better, and also we can just learn how radio waves travel, how radio waves propagate. Digital cameras, how do we deal with taking live sporting events? Those things have trickled down as a result of looking into space and using telescopes.
The telescope, truly a wicked invention. Can we create a telescope from a crisp tube? We're going to need an empty crisp tube, black A4 paper, scissors, pliers, gaffer tape, and 2 magnifying glasses. Ideally, one should be smaller than the other, and they both need to be no larger than the diameter of the crisp tube. To begin, take the A4 black paper and create a tube that has a diameter that is just a little smaller than the crisp cardboard tube so it can slide snugly inside. Remove both ends from the crisp tube and fix the larger magnifying glass to one of the ends. Fix the smaller magnifying glass to one of the ends of the paper tube. Slide the paper tube into the crisp tube and you are ready to go. We point the telescope at an object and adjust the distance between the 2 lenses until we can see a focused, magnified image, although it is upside down. As we've seen earlier, light from an object hits the first lens and gets bent. By using a second lens, the light gets concentrated, so we create a brighter, magnified and inverted image. Can we create a telescope from a crisp tube? Yes, we can. We can challenge smashed. What's the link between coloured pencils and the ancient empires of Greece, Egypt and Rome? There's little doubt that at some point in our childhood we've picked up a colouring book and coloured pencil. But of course, these little sticks of colour aren't just for kids and have become popular with many artists. Unlike standard graphite and charcoal pencils, coloured pencils are made of a narrow core of coloured wax or oil, cased in a wooden cylinder. Although the history of the coloured pencils we see today isn't entirely clear, the idea of combining wax with a pigment dates back thousands of years. The Roman scholar Pliny the Elder was the first person to describe a particular painting technique called encaustic painting. This technique involves combining hot beeswax and a coloured pigment to form a paste, a bit like thick paint. The paste is then applied to a surface such as wood or canvas. The ancient Greeks and Romans both painted using this encaustic technique, as well as ancient Egyptians. This kind of painting produces artworks that are extremely durable and can stand the test of time. Possibly the most notable surviving example of this comes from the Fayum mummy portraits of ancient Egypt. Unlike coloured pencils, encaustic painting involves a paste and tools to apply the paste to the surface. It wasn't until centuries later, in the 1800s, that coloured pencils appeared, offering a way of colouring all in one tool that could be held in one hand and carried around easily.
Pencil that we know and love certainly developed in the 19th century, and it was a inventor stationer Stapler, who came up with the first of coloured wax in 1834, but actually this was more of a crayon coloured. And then it was later that sort of developments continued and you got competing companies all trying to beat one another.
These first coloured pencils were mainly just used for the checking and marking of documents and work rather than for art. It wasn't until the 20th century that the first coloured pencils used for art went into production. However, since then, they have become a mainstay in classrooms and artists' pockets worldwide.
There's the colouring pencils that you and I would have grown up with at school, playing at home, but then there were developments in the artist quality colouring pencils. And then there were things like Derwent colouring pencils, they came up with the sort of original 24 different colours in the 1930s. But then by the 1990s, you had something like 120 different colouring pencils.
So, how are these wicked inventions made? The life of a coloured pencil begins with the 2 main raw materials. These are wooden slats and the leads. Although still called leads today, these pencils actually use a combination of graphite and clay. The graphite creates the marks on the paper, whilst the hard clay provides strength and substance. Different mixtures of the two materials can be used to create different pencil hardnesses for a variety of applications. These leads can be mixed with coloured dye to create a whole range of coloured pencils.
The color leads are nearly produced in an equal way. Instead of graphite, you use a certain amount of pigments, which are different, of course, from color to color. And you have some binding components that you also put into the paste of the leads.
Other than mixing in the colours, the production of a coloured pencil follows the same process as a standard pencil. The cedar wood slats are supplied ready and form the basis of the pencils. Grooves are cut into the slats and a special glue is then added into these grooves to keep the leads in place. A metal wheel then places each of the leads of the pencils in these grooves. A second groove slat is placed on top to create something resembling a lead sandwich. These sandwiches are then dried in a hot air drum for about an hour to ensure the glue is properly set. A planing machine then cuts the slats into individual pencils. Each of these sandwiches can produce up to 10 pencils at a time. The pencils are then given a protective coating made from water-based paint. Each pencil is coated several times in order to create the perfect finish. The pencils are then foil stamped with their relevant hardness and logos. Next up, once the pencil ends have been cleaned, it is the dipping process. This essentially paints and protects the ends of the pencils. They are literally dipped in a shallow bath of paint to accurately cover the pencil ends with just the right amount of paint. Of course, some pencils need erasers fitting. This is done next on all of the relevant pencils in another machine automated process that's able to fit these erasers at great speeds. A huge pencil sharpener of spinning sandpaper then sharpens all of the pencils to the perfect point. This machine is able to sharpen many pencils at once, much faster than any of the pencil sharpeners we might be familiar with at home. The next stage is the quality check, all done by the trained eyes and hands of an operator. Using their experience, they ensure that no imperfect pencil ever leaves the factory. Once the quality control check is complete, the pencils are boxed up and sent out all across the globe, ready to be put to use by keen writers and artists alike.
We have around 120 countries where we are sold. We produce 2 billion black lead and color pencils per year. If you lay them end to end, then it would go 10 times around the equator. That is the annual production.
Pencils, truly a wicked invention. So, there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Whiskey, telescopes and coloured pencils, all wicked inventions.